Hello everyone. Today we are going to talk about section 5.1. We are going to start chapter 5. Unfortunately, we are going to cover probably just one section of it. We are going to talk about eigenvalues and eigenvectors. Let's start with a definition. So, definition tells us, consider square matrix A with size n by n, and consider some vector x which belongs to n-dimensional space. If you multiply matrix A by z vector x, and the result is kind of proportional to the same vector x, where coefficient of proportionality just a real number, then we are going to call this vector x eigenvector of matrix A. And the value lambda we are going to call eigenvalue. Well, what does it mean on practice? Imagine that we have vector x, and vector x looks like this. Well, again, I'm using two-dimensional vectors, but it's not necessary, just like visualize a definition. Imagine that we multiply this vector x by some matrix A. When you multiply vector x by some matrix A, because matrix is n by n, result is going to be another vector with dimension n. And it can go in any directions. It can, like, the result can go like this, can go like that, can go like this, like any, like, in this case we have two-dimensional vectors, so the matrix is going to be 2 by 2, and the result can be any vector 2 by 2, right? But imagine that we have the resulting vector ax just kind of parallel to our vector x. So you multiply matrix A by vector x, and the resulting vector looks like this. And if you look at vector x, well, it's going to be exactly parallel. You know, when two vectors are parallel, they are proportional with some coefficient of proportionality. So we are going to say that ax, my new vector, is proportional to my original vector x with coefficient of proportionality lambda. On my picture, it's 2 actually. Lambda equals 2. So if I take vector x multiplied by 2, I'll get the resulting vector ax. Well, again, this lambda is called eigenvalue, and vector x is called eigenvector. The question is, well, do we have actually lots of vectors like x for matrices? Like, can any vector work? Well, we do know that any vector is not going to work. You just can take any arbitrary vector, multiply it by matrix 2 by 2, and you are going to get a totally different vector, not parallel to original one. But actually, there are some vectors which are going to stay parallel to original one when you multiply it by matrix A. So in this section, we are going to learn how to find them. So basically, guys, we are going to solve a problem of finding eigenvectors and eigenvalues of a matrix A. Before we start considering real examples, I want to write down this statement, which is kind of definition, as an equation. I'm going to write it down like ax equals lambda x, right? And because I'm planning to move ax to my right side of equation, I'm going to get something different. I'm going to get lambda x minus ax. Well, I'm trying to solve it as a regular equation, combine everything on one side of the equation, just combine together. Well, here it would be very nice to take x outside of parentheses, right? Because that's a simple same multiple here and same multiple here. The only bad thing which is not allowing us to do this is that if we take x from my first term, we're going to have just number. And if we take x from my second term, we are going to have matrix. So generally speaking, we cannot subtract matrix from just a number. So what I'm going to do, guys, I'm going to turn this just a number into a matrix 2 by inserting over here identity matrix. You know that if you multiply identity matrix by x, you are still going to get x. So basically identity matrix is present in every vector x. And after that, we can take x outside of parentheses. So we can write down in parentheses lambda I here for the second term a, and outside of parentheses x. And that's going to be equal to 0. And I'm sorry, I'm missing vector bar 0. Well, it's kind of similar to trying to take outside of parentheses something like this. You have, for example, 2 minus 2x. If you want to take 2 out of parentheses, what is going to be left here instead of 2? There is nothing else besides 2 here, but we always think that 2 can be represented as 2 by 1. And if you take 2, it's not like nothing is left. It's actually 1 is left. Well, this 1 is actually identity matrix here, working like 1, Trying to explain how that equation is built. Now, guys, what we have actually, we have a homogeneous equation, right? That's a homogeneous equation. Homogeneous equation looking like this. Bx equals 0. Well, my B matrix is actually like this compound, the whole parenthesis. And when homogeneous equation has non-trivial solution? Well, you probably remember from the previous chapter that for homogeneous equation to have non-trivial solution. Non-trivial solution. We're supposed to have determinant of the matrix B equal to 0. Well, you probably remember why does it happen. If determinant is not equal to 0, all rows of matrix B or all columns of matrix B are linearly independent. And if they are linearly independent, then there is only trivial solution for linear combination. And solution is actually going to be this axis. But if they are linearly dependent, we are going to find non-trivial solution. And there is going to be something like non-trivial solution. In our case, because matrix B is this compound, I'm going to write it down like this. Determinant of lambda I minus a must be equal to 0. Again, to get a non-trivial solution. For x non-trivial solution. Why do we need non-trivial solution? Let's look at the definition. Definition tells that we are going to call vector x eigenvector only if it's not equal to 0. So we are searching for non-zero solutions here. Okay, so we have a determinant of this matrix equals to 0. And this equation is called characteristic equation. And right now it looks like some kind of matrix equation, but actually it's not. It's just a polynomial equals to 0. I'm going to show you example of solution and you are going to see everything yourself. So let's consider matrix A looking like this. I'm going to consider example number 1. Let's consider matrix A looking like this. 3, 0, 8, minus 1. And the question is, usually find eigenvalues. And eigenvalues are lambdas and eigenvectors. And their axes. So how are we going to do it? First, we are going to build this characteristic equation. And it's going to look like we have matrix lambda I, which is 1, 0, 0, 1, right? Minus matrix A. Well, I'm just going to copy matrix A. I'm not going to write down A. I'm just going to copy it. Something like this. That's matrix A. So this lambda I, this part is lambda I, and this part is just A, and I'm just subtracting them. So first I'm calculating actually that matrix in determinant, and then I'm going to do the determinant. So when we subtract two matrices, we are just subtracting them entry by entry. So we have lambda minus 3. I'm going to write down lambda minus 3. And next term, lambda by 0, which is 0, minus 0, which is also 0, still 0. Lambda by 0, minus 8, just minus 8. And lambda by 1, minus 1, plus 1. So that's going to be my matrix. And basically, the equation eventually we are going to solve is going to look like this. So lambda minus 3, 0, minus 8, lambda plus 1 by x equals 0. I'm going to put over here that this is equation lambda I minus a by x equals 0. That's the equation we are actually solving for lambdas and for x's. Well, you see, it's interesting that we do have two kind of variables here, right? We have eigenvalues, which are lambdas, and eigenvectors, which are x's. My lambdas don't look like very nice lambdas. I'm going to write it down like this. Okay. Well, now we'll need to set up the determinant equals to 0, right? Determinant of what? Determinant of this. So determinant of this matrix supposed to be equal to 0. Well, I'm going to calculate determinant. Because it's 2 by 2 matrix, I'm just going to do like lambda minus 3 by lambda plus 1 and minus 0 multiplied by negative 8. Well, looks like we are going to just have lambda minus 3 lambda plus 1 equals to 0. So you see that determinant or characteristic equation, let me go over here, characteristic equation, that's not actual matrix equation. That's just like some quadratic equation or some polynomial equation. Well, what are going to be solutions in this case? Solutions in this case are very obvious, and they are going to be lambda 1 equals 3, right? Turns into 0. And lambda 2 equals minus 1. Are we done? No, guys. So far, let me go a little bit back. So far, guys, we found eigenvalues. Now, we will need to find eigenvectors. What are eigenvectors? They are actually, well, those axes which kind of correspond to the lambdas. So what I'm going to do, guys, I'm going to take this first lambda and plug it into this equation. Well, lambda I minus a. So I'm searching for this one. I already know these ones. I already know them, so I'm searching for this one. So let's start with first lambda and do it. I'm going to do it over here. So 3 minus 3 is 0, 0, minus 8, and 3 plus 1 is 4, right? By some x equals 0. So that's my homogeneous equation. Well, it looks like I totally miss the first row, right? And my second row is going to be the only one essential here. So, well, since I have only one row, I'm going to have only one leading variable and one free variable. I'm going to set up x2 equals t. Then, what is going to be then x1 from equation number 2? Minus 8x1 plus 4t equals 0, from where x1 equals what? 4t over 8, which is 1 over 2t. And my final vector, x1, x2, is going to look like what? 1 over 2t, t. And if I take t outside, it's going to be 1/2 and 1 over here, right? And that's going to be my first eigenvector. Guys, because t is arbitrary constant over here, I can kind of think that it's not just t, but 2t, let's say. And if I think it's 2t, if I kind of consider this one is 2t, I can take this 2 and multiply by each entry in my vector, and I'm going to get that x1, my first eigenvector, equals 1, 2. I multiplied each entry by 2, and I'm going to put over here t. So that's going to be my first solution. So my first eigenvector. Usually, well, you don't need to write down t, but actually maybe t is just going to give us the idea that we can stretch this vector by any number. Okay, now, so we are done with my first lambda. Now we have to repeat the process for second lambda, for this one, right? And for this lambda, I'm going to, maybe I should change the color so you can kind of see the difference. So I'm solving it for my second lambda. And I need to plug second lambda into my same equation. So I have minus 1 minus 3, which is minus 4, still 0, still minus 8, and minus 1 plus 1 is 0. So I have the next equation. Again, this is x vector, but it has two kind of components, x1, x2, right? Because it's two-dimensional vector. So guys, what do we see here? We do see that here we are missing the full column. In previous one, there was a row missing. Here we had row missing. Here we have column missing. What does it mean? Well, it still gives us one leading variable. You can use, for example, x1, right, and one free variable, x2. Just because row number 1 and row number 2, if you look at them, they are proportional, right? If you multiply row number 1 by 2, you get row number 2. This is always going to be the case when you plug in lambdas. Why? Because the idea is to make determinant equals to 0, and you can make it only if one of the rows is proportional to linear combination of others. Well, because we have just two rows here, now like one of them is going to be proportional to a second one. Right? Okay, so here guys, I'm going to choose x2 as my free variable. Well, I don't know, let's use letter P. What is going to be my x1? Well, if I use the first equation for x1, it's minus 4x1 plus 0p equals 0. Well, what is going to be solution here? By what should I multiply minus 4 to get 0? Well, by 0, so x1 equals 0. So my solution here is going to be x1 equals 0, x2 equals p. If I write it down as a vector with p like parameter, it's going to be 0, 1, right? And that's going to be my vector x1, x2, or my second eigenvector. Okay, so we finished our solution. I'm going to write down the answer. The answer here is not going to be short, and let me use a different color to write it down. So, answer, how the answer is going to look. Lambda 1 equals what? Minus 3, right? Or not 3. And x lambda 1, the first eigenvector, is going to be t 1, 2. Lambda 2 equals minus 1. X, which corresponds to the second eigenvector, is 0, 1. Okay, so we have two lambdas and two vectors. Very good. Well, that was just an example. Now let's kind of talk about some general properties of lambdas, or what can make our life easier, some theorems or some theory about this, all these eigenvectors and eigenvalues. So, guys, what do we have in general? You probably have seen that from matrix 2 by 2, we got a quadratic equation for lambda. Let me just point, like, from matrix 2 by 2, we got equation where maximum degree of lambda was 2. From n by n matrix, degree of lambda is going to be n. So, generally speaking, guys, in general, we are going to have a polynomial depending on lambda, and it's going to have the greatest power of lambda, and then c1 lambda to the power of n minus 1, and cn minus 1 lambda, and the last one is going to be cn. Okay? So, I'm going to write down for a n by n. Well, I'm not going to prove it, but it's easy to see that because you have lambda once in every row. When you do the determinant, even like by row expansion, you are going to have kind of from like, remember by row expansion, you are decreasing matrix by one size every time you do row expansion. So every time you are going to have one extra lambda in this equation. Like you consider the first row and you are going to have a lambda multiple somewhere. And then you kind of do determinant of a smaller matrix and you are going to get a lambda again. Maximum amount of lambdas you can have is n. So we are going to have a polynomial of n degree. By the way, guys, what is going to be, well, this characteristic equation is what? It's a determinant of lambda I equal minus a, right? So if you consider this determinant, you are going to get this. Yes, I want to point onto one interesting detail of this polynomial. This usually that's a polynomial, but we are turning it into 0 to get some non-trivial solution for x's, right? Let's imagine, let's set lambda equals to 0 on the left side and on the right side. What are we going to have here if lambda is equal to 0? Well, if lambda is equal to 0, I'm going to get 0 plus, second term is 0 plus, the only term which is going to be left is cn, because all other terms are multiplied by lambda and it's going to be 0. So what we are going to have here, guys? Well, if you set up lambda equals 0 here, you are going to have a determinant of matrix minus a. You see? So basically, term cn is equal determinant of matrix of minus a. Depending on the size of matrix minus a, remember when you put minus in front of matrix a, you are kind of doing -1 on every entry of that matrix. And if you do that, you are going to have -1 to the power of n determinant of original matrix. Remember that when you kind of multiply matrix by a number, you kind of have the multiplication by that number n times multiplied by determinant. So I'm going to write it down that Cn, the free term of my equation, is always going to be equal to -1 to the power of n determinant of matrix A. So they are connected. The free term of the polynomial is connected to determinant of A. It's actually equal it with like by absolute value. So you can write down that absolute value of Cn equals absolute value of determinant. And this way you don't need to worry about minuses. So numbers are going to be equal. There's going to be either minus or no minus, but like, okay. Okay, that's just one observation, which we are going to eventually use to prove a theorem. That the free term is equal, like, determinant of A with plus or minus. Okay. Now, guys, remember that somewhere, like in chapter 1, we considered matrices which were diagonal or upper triangular or lower triangular. So, how equation is going to look on them? Well, for example, how equation lambda I minus A is going to, like, determinant equals to 0 is going to look on upper triangular matrix. I'm going to just literally write it down. So I'm going to have, imagine that we have upper triangular matrix. Upper triangular matrix is going to look like this: A11, A12, and here 0, A22, and here 0, 0, A33, and so on. And basically you are going to have all zeros here and probably some numbers here, maybe even zeros here, A and N. That's upper triangular matrix, right? Which is looking like a triangle. Okay, so now if I apply this equation to it, I'm going to have lambda minus A11 and then minus A12 and so on. And here 0. Well, that's just because, like, this is identity matrix, and you basically are going to modify only diagonal elements. Lambda minus A22, and then A23 minus and 0, 0, lambda minus A33, and so on. Well, guys, what we are going to see? What is going to be the determinant of this matrix? Well, we remember that for upper triangular matrix, it's still upper triangular. The determinant is the product of diagonal elements, right? Because if you do expansion by, for example, the first column, you are going to get this. So determinant of this matrix is going to be lambda minus A11, lambda minus A22, and lambda minus ANN. So actually, when you set it up to 0, you are going to get a very, very simple equation, which is going to consist out of only like product of parentheses, and you can solve this equation right away. You can say that first lambda is A11 and the second lambda is A22 and so on. So basically, guys, for upper triangular matrix, lambdas are just diagonal elements. So lambdas are diagonal elements. Well, what is going to happen for lower triangular matrix? Well, because it still has lots of zeros and only diagonal elements are going to be affected, the determinant is still product of diagonal elements, and lambdas are still going to be diagonal elements. And if your matrix is just diagonal matrix, well, it has no elements above or below diagonal, you are going to modify only diagonal elements, and eventually determinant is going to be looking same. So these three matrices are very good to calculate lambdas. You don't need to solve anything actually. You just kind of use diagonal elements and they are going to work as lambdas. I'm going to consider example just to show you, because it's actually in the book, it's a theorem, but that makes too simple for a theorem. So I'm going to consider example number 2. Let's imagine that our matrix is A, and that's a lower triangular matrix, and that's going to look like 1, 0, 0, 5, 2, 0, and 7, 8, 3. So it's lower triangular matrix, and it has diagonal elements 1, 2, 3, and has non-diagonal elements. So from kind of this consideration, we know that lambda 1 is going to be equal to 1, the first diagonal element, lambda 2 is going to be equal to 2, and lambda 3 is going to be equal to 3. So diagonal elements. Okay, so basically something with diagonal elements is very easy to kind of calculate eigenvalues. Okay, besides eigenvalues, we will need to know eigenvectors like x1, x2, and x3 for these three, right? Well, before we calculate them, or I would rather consider a different matrix to calculate. I was using this as example. The space or span of these eigenvectors is called eigenspace. So in the book, they call it a null space of lambda I minus A matrix. Well, you remember that null space is a solution. Null space is a solution of homogeneous equation, right? Null space is a solution of homogeneous equation, or null space of this matrix, modified one, not actual matrix A, but matrix lambda I minus A, null space. Well, we're going to call it eigenspace. Well, eigenspace is going to consist out of eigenvectors and all possible combinations of them. I want to consider another example, more convenient one for finding eigenspace, and I'm going to consider upper triangular matrix. Well, again, just because I don't want to solve long equations, so my matrix is upper triangular, and that's going to be 1, 2, 3, 0, 2, 4, and 0, 0, 2. Well, again, upper triangular matrix, and I know that my lambda 1 equals 1, my lambda 2 equals 2, and my lambda 3 actually also equals 2, right? My diagonal elements are 2, 2. We're going to say that lambda 2 equals 2 has multiplicity 2, repeated 2 times, multiplicity. Well, what does it mean for us? Well, less actually solution needed, just because you don't need to substitute lambda 1, lambda 2, lambda 3, but you substitute only lambda 1, lambda 2, and find solutions x. Let's do it. So let's try to now solve this lambda I minus A x equals 0 system. So I'm going to use lambda 1, which is equal to 1. So what I have? Well, 1 minus 1 for the first element, then minus 2 minus 3. 0, 1 minus 2, minus 4, 0, 0, and 1 minus 2. And that's supposed to be x equals to 0. I just plugged in, I just made up this matrix, lambda minus, and subtracted all elements of matrix A. Right, so what I'm going to have, I'm going to continue my solution on the right. What I'm going to have 0, minus 2, minus 3, and here 0, minus 1, minus 4, and here 0, 0, minus 1, right? And that's going to be x equals to 0. Well, what is going to be a solution of this? Well, you see that we do have like one column total equals to 0, right? And you probably are going to think, well, it doesn't look very obvious that this one of these rows is going to be linearly dependent on another one, right? Well, we can kind of show that, or well, we can actually maybe just use our leading elements. Well, here, guys, to do it formally, we will need to maybe kind of turn this one into 1 and then kind of do this elimination. We should do it just to show it once in a while, like. But normally, guys, if you can guess about solution, that's fine. I'm going to do elimination, so you are going to see that it's going to work. Okay, so let's do it. So 0, well, multiplying by -2 here, by -1/2, 1, and -1/2 is 3/2, right? And here 0, -1, -4, and 0, 0, -1. My next modification is going to be row number 2 equals row number 2 plus row number 1. So I have 0, 1, 3/2, 0, 0, and -4, -4 plus 3/2 is going to be 5/2 minus 5/2, right? And I have 0, 0, -1. Well, now what I can do, I can turn this into 1 by just multiplying row number 2 by -2/5. Oh, sorry, I'm going to move here a little bit. I'm just doing it formally, but it's not necessary. So -2/5. So what I'm going to have? As a result, I'm going to have 0, 1, 3/2, 0, 0, 1, 0, 0, -1. Well, I'm doing it only once, guys. You don't need to kind of check it. If you found lambda, it's going to mean that, well, one row is going to be dependent, at least. Well, now you can eliminate this -1 by adding row number 3 equals row number 3 plus row number 2, right? And I don't want to kind of copy everything. I'm just going to put 0 here, because when I do that, it's going to turn into 0. So this row is going to be row of zeros. And what I have leading variable here, and I have leading variable here. I don't have anything over here. That's going to be my free variable. And I'm going to say x3 equals t. No, sorry, x1 equals t. x1, the first variable, equals t. x2 equals what? Well, I actually need to write on x. Maybe I should. Give me a second. What I have for x2, this equation is, no, that's not x2, x3. x3 multiplied by 1, these twos are zeros and equals to 0. Obviously that x3 from this equals to 0. And x2 is going to be found from this equation. So x2 plus 3/2, 0 equals also 0. So what is going to be a solution for x2? Well, the only solution for x2 is going to be also 0, right? So what we have, x1 equals t, x2 equals 0, and x3 equals also 0. And as a vector form, it's going to be 1, 0, 0 multiplied by t. That's my eigenvector, which corresponds to my first eigenvalue, which was lambda equals 1. Well, we still have the second eigenvalue, which is lambda equals 2. Well, kind of long way to go. But I'm going to do lambda equals 2, and I'll need to substitute it again into my system. And I'm going to do it. So lambda equals 2 is going to give me 2 minus 1, which is 1, minus 2 minus 3. I'm going to modify only diagonal elements. 0, 0 here, right? 2 minus 2 is 0, minus 4. And 2 minus 2. Here instead of 1, I'm going to have 2. 2 minus 2, 0. Well, that's what I have. X equals to 0. Here I don't think that I'll need even modify it. I do see that I have one leading variable here and one more leading variable here. I don't have anything over this position, so x2 is going to be my free variable t. Or you can use a different letter. I already used t over here. I'm going to use p. Though it's not necessary, but let's use p. What is next? Well, next is going to write down the second equation, and that's going to be minus 4x3 equals to 0, right? Just 0, 0, minus 4x3 equals to 0, from where x3 equals to 0. And the first equation is going to be x1 minus 2 multiplied by 0 minus 3. Oh, no, 2 multiplied by p, sorry. Did too many. 2 multiplied by p, my second variable, and minus 3 multiplied by 0, supposed to be equal to 0. Well, this one is 0. I have 2 3's somehow. I was not supposed to have this double 3, right? Minus 3 multiplied by 0. And what I have for x1 is x1 equals 2p. How my solution is going to look? x1 equals 2p, x2 equals p, and x3 equals 0. If I take p outside, I'm going to have 2, 1, 0. 2, 1, 0, and that's going to be my second eigenvector, x2, which corresponds to lambda equals 2. You see, despite the fact that we had multiplicity 2, we got just one eigenvector, and that was 2, 1, 2. And the first one was, let me kind of move it here so you can see them both at the same time. The second one was here, and I'm going to write down x1 is going to be t 1, 0, 0, and that would correspond to lambda equals 1. Well, we solved the problem. Okay, what else do we need to know? Well, 2 more theorems and we are done. Give me a second. Well, the first thing I want to kind of investigate also, what are going to be eigenvalues of powers of A? Like, for example, what are going to be eigenvalues of a square or a cube? Well, let's do a square. So a square x is going to be equal to what? If you know eigenvalue, for example, if you know that ax equals lambda x, you know eigenvalue of the first power, then you can kind of write it down. A by ax. And we know that ax is lambda x, so you can write down a lambda x. Lambda is just a number. You can always take it outside of the matrix, and that's lambda ax. And ax again equals lambda x. So we have lambda by x, which is going to give us lambda square x. So basically for the square of a matrix, eigenvalue, I'm going to put it tilde, it's going to be a square of eigenvalue of singular matrix, not squared. And the cube is going to be a cube. Well, it's just to know. I don't think that you are going to use it unless like you kind of going to we'll go deep into solving eigen theory equations. Now the last theorem. Square A is invertible if and only if lambda eigenvalue of this matrix are not equal to 0. So you don't have 0 eigenvalue. Not an eigenvalue. So square matrix is invertible. And I'm going to put here if and only if. So that's how we pronounce this two directions arrow. So matrix is invertible if and only if lambda equals 0 is not an eigenvalue. Well, how are we going to prove it? Well, from some previous my pen is getting worse. From some previous lecture, I think that was chapter 1. We know that A is invertible if and only if determinant of A is not equal to 0. So if determinant is equal to 0, it's not invertible. Invertible if and only if, right? On the other hand, guys, we know that for this characteristic polynomial p of lambda, which is like lambda to the power of n plus plus cn equals actually what? Determinant of lambda I minus a equals to 0. We do know that the cn actually equals to determinant of minus a, right? Determinant of minus a equals cn. And we do know that this determinant is also like minus 1 to the power of n determinant of a. Sorry, kind of messy here. So we know that Cn actually is that's determinant of A. So basically, matrix A is invertible if determinant is not equal to 0 or if Cn is not equal to 0. Just because Cn equals to that determinant. Well, you know that if determinant is not equal to 0, then Cn is not equal to 0 here. Well, when Cn is not equal to 0, let's look at this equation. This is just a polynomial equation, right? Just a polynomial equation. It has some solutions. Imagine that lambda equals 0 is a solution. Then what is going to happen? If it's a solution, it's turning into a true statement. So P of 0, if lambda equals 0 is a solution. Then P of 0 must be equal to 0. But if you plug in 0 into all these lambdas, you are going to get a Cn, the last term, which is not multiplied by any lambda. So if lambda is a solution, then Cn must be equal to 0. But if matrix is invertible, then determinant is not equal to 0, then Cn is not equal to 0. And then lambda is not going to be a solution just because we know that it's not equal to 0. Not equal to 0 means that it's not a solution. Well, kind of strange proof. Actually, we are proving both directions simultaneously. Usually, remember, I always prove like this way and this way separately. But here, we are making equivalency statements every time. Equivalency statement here, matrix is invertible, then equivalency statement, determinant is not equal to 0. Determinant is not equal to 0, then Cn is not equal to 0. Cn is not equal to 0, then lambda is not equal to 0. Last equivalence statement. Lambda is not equal to 0. Because if lambda is equal to 0, then Cn equals to 0 and nothing works. You see? Okay. We proved that theorem. Well, guys, that sounds like lecture is too long already. I think I'm going to consider one example, but I'm going to consider it as a separate video. Otherwise, that's just like going to probably last forever. Or maybe just 5 more minutes and I don't need to record another video. Okay, let's do one example, though it's already 45 minutes. I don't remember a number of my example. I think it's probably example 4. I'm going to consider like just a full problem. Somebody gives me matrix A with like some coefficients. And they are asking lambda and x lambda, the short way to write down eigenvectors and eigenvalues. Something is happening with my electronic pen. I think I kind of broke it probably, or something like this. Okay, so how do we solve it? Well, first we are going to do this determinant, right? Determinant of lambda minus 4, 0, 1, 0, lambda minus 3, 0, minus 1, 0, lambda minus 2. Well, this matrix is not supposed to be very complicated, so I'm going to just do a standard row expansion. So lambda minus 4, and determinant of remaining matrix is actually lambda minus 3 by lambda minus 2, because there are 2 zeros here and here. And then, the next element is going to be plus minus plus, and it's going to be one by, and determinant of remaining matrix is 0 minus this minus 1 multiplied by this. So 2 minuses, it's going to give me plus. So it's going to be lambda minus 3 by 1 more 1. Okay. Well, supposed to be equal to 0. What I see, guys, I see that I have same parentheses here and here. I'm going to actually take it outside. I'm going to write down lambda minus 3. Maybe I should not write down equal sign because I make it like equation already. And in parentheses, I have lambda minus 4 by lambda minus 2. Sorry, my lambdas are looking like x's. Even worse. Lambda minus 2. And from this one, the only thing which is going to stay is 1, right? I mean, just like lambda minus 3 goes outside of parentheses, and the remaining thing is just 1. Well, what I'm going to do, guys, I'm going to probably open this parenthesis. I'm going to work a little bit with this equation. As I promised, the problem is not supposed to be too long, so it's going to be lambda squared minus 6 lambda plus 8 plus 1. Yeah, I see where it goes. So, guys, it's lambda minus 3. What I have in this parenthesis is lambda squared minus 6 lambda plus 9. You guys probably recognize a perfect square over here, which is lambda minus 3 squared. That's a perfect square. Oh, just open perfect square, you're going to see that coefficients are same. So, very nice. So, I have actually lambda minus 3 cube equals 2, 0. Which is going to give me only one lambda solution, lambda 1, which is going to be equal to 3. And multiplicity of this solution is going to be also 3. Give me a second. This 3 doesn't look very nice like 3. Okay, now we just need to plug in this lambda and solve the actual equation. Well, maybe I should start doing it over here. So if I plug in lambda 3 over here, I'm going to get minus 1, 0, 1, 0, 0, 0, minus 1, 0, and over here 3 minus 2 is 1. And I'm supposed to multiply it by x1, x2, x3, and I'm supposed to get 0. 0, 0, 0. You guys probably see that row number 1 and row number 3 are identical rows. So you can eliminate it, which means that you have only one leading variable, which is kind of x1, right? And 2 free variables. So x2 equals, for example, p, and x3 equals, for example, t. 2 free variables. Let me kind of point. Free. Okay, well, again, you can just eliminate this one by adding to row number 1. Now, what is going to be x1? Well, x1 actually going to be what? I'm going to write down the equation for x1 so you can see it. Minus 1 x1 plus 0 multiplied by p x2 plus 1 multiplied by t is supposed to be equal to 0, right? Up the first equation. Well, what I'm going to get from it? This one is 0, right? And I have x1 equals minus minus equals t. Well, I'm going to just write down the answer over here. And how do I write it down as a vector? You see that I have p and t, different kind of parameters here. I'm going to separate them into two vectors. Watch how I do this. I'm going to write down t, and then 1t here, 0t in the second variable, and 1t here, right? Plus p. And I'm going to have 0p in the first one, 1 in the second, and 0 in the third. And these are going to be like my eigenvector. So my eigenvector, I'm going to write it down somewhere separately, is going to consist out of two vectors. Why did it happen, guys? Because we have high multiplicity of my eigenvalue. 0, 1, 0, and lambda equals 3. So these are going to be my eigenvectors, or my actually one eigenvector, which consists out of two. And it's going to produce some eigenspace, right? Eigenspace is going to be space based on these two vectors, 1, 0, 1 and 0, 1, 0. Well, that's it. Dimension is what of this eigenspace? 2. And like that's a typical problem. Okay, I promised 5 minutes. I already used 6. Sorry. I think that's the end of this section. Thank you very much.